Now Habers process, that is manufacture of ammonia. We are explaining it in terms of equilibrium. See, equilibrium is a term that is applied to reversible reactions, and equilibrium means it's a stage of reaction in which the rate of forward reaction will be equal to rate of backward reaction, and the concentration of reactants as well as the concentration of products are not going to change, because rate of forward reaction is equal to rate of backward reaction. That is the meaning of the term equilibrium. Now first of all, let's see what this chemical reaction is for the manufacture of ammonia. This reaction is quite simple. Nitrogen N2 is combining with hydrogen H2. The reaction is reversible. It is going to produce ammonia, which is NH3. Reaction is quite easy to balance. This will be 2 and this is going to be 3. Okay. Now, at the stage of equilibrium, the rate of forward reaction will be equal to rate of backward reaction. So the concentration of nitrogen and hydrogen, which are the reactants, will remain unchanged, as well as the concentration of ammonia that is already produced, that is also going to remain unchanged. Now, what are the factors that are going to affect this equilibrium? We can control or we can shift the equilibrium either to left or to right. Now this you will have to consider in two terms. One is in terms of pressures and volumes, and second thing is in terms of temperature. Now we'll consider here, because all of these three reactants are gases, so we'll consider the mole ratio in terms of gases. This is 1 volume, this is 3 volumes, and this is 2 volumes. Okay, so the total volume of the reactants is 4 volumes, and total volume of the product is 2 volumes. So whenever the forward reaction is proceeding, it is going to proceed with decrease in volume. It means when forward reaction is taking place, the volume is getting decreased. If I'm applying high pressure, okay, this part is very important. If I'm applying high pressure, I'm trying to decrease the volume, I'm trying to compress the reaction mixture. It means I'm helping the reaction to take place. Why? Because the forward reaction is proceeding with decrease in volume. By applying high pressure, I'm also trying to decrease the volume. So if I apply high pressure, this is going to favor the forward reaction. More formation of ammonia is going to take place. When I say more formation of ammonia is taking place, it means the equilibrium is shifting towards right, because this ammonia is on the right hand side. Okay, so high pressure forward reaction, I'm going to get more of ammonia. Yes.
So, but like this, even nitrogen and the hydrogen will increase, not the pollution. Like
No, see, if I'm applying more pressure, you see here the pressure is increased. When you are going to increase the pressure, I'm shifting the equilibrium towards right. It means I'm going to get more of ammonia. The amount of nitrogen and hydrogen is going to reduce. The concentration of nitrogen and hydrogen is going to reduce, so that if I put more nitrogen and hydrogen in the reaction mixture and apply more pressure, I'm going to get more of ammonia. That is what we are supposed to do. So high pressure favors forward reaction. The equilibrium is going to get shifted towards right. I'm going to get more of ammonia. And conversely, obviously, if we are having low pressure, then more of nitrogen and hydrogen will be obtained, which we don't need, because we are carrying out here manufacture of ammonia. Therefore, high pressure is going to favor the forward reaction. So in this process, high pressure is a preferable factor to get more of ammonia. Now the second factor that we are going to talk about is about temperature. Now when we talk about temperature, we must know whether the reaction is exothermic or endothermic. Okay, now here the value of delta H is negative. Okay, the value of delta H is negative. It means this reaction is an exothermic reaction. When the reaction is exothermic, it tries to give out heat energy. I repeat, when the reaction is exothermic, it tries to give out heat energy. So if I use high temperature, it means I am also applying heat to it. I am also trying to heat it up while the reaction is trying to give out the heat. It means I am trying to oppose the reaction. So if the reaction is exothermic reaction, then low temperatures are going to favor the forward reaction. I'm repeating the last part once again. If the reaction is exothermic, then the forward process is trying to give out heat energy. If I am using high temperature, then I am also supplying heat to the reaction mixture. It means I'm not allowing that heat to come out when the forward reaction is taking place. It means I'm opposing this reaction. It means if I'm going to use high temperature, this is going to favor the backward reaction. So for exothermic reactions, we need to use generally low temperature. But again, here the problem is nitrogen and hydrogen, both of these are very less reactive gases. First of all, in order to make react nitrogen and hydrogen, both of these reactivity is very less. Nitrogen is already having a triple bond. So first of all, if I have to make this react with hydrogen, first I have to break this triple bond also. It means some amount of high temperature or moderate temperature will be required. This temperature that is required is known as optimum temperature. This optimum temperature is about 450 degrees Celsius. Okay, it means in terms of industries, 450 degrees Celsius is not very low temperature also, and it's not very high temperature also. This temperature that is required is called optimum temperature. That is, it is moderate temperature. You need to know this term. What is it called? It is optimum temperature. Also, you need to know how much the temperature is, which is 450 degrees Celsius. It means if I'm going to use very low temperature, just 1 second, let me finish. If I'm going to use very low temperature, then nitrogen and hydrogen will not react at all. If I'm going to use very high temperature, say 700, 800 degrees Celsius, in that case, because the reaction is exothermic, I'm not allowing that heat to come out. Instead of that, I'm trying to heat it up. So I'm favoring here the reverse reaction. So in order to maintain this balance, I'm using this average temperature, moderate temperature, that is optimum temperature of 450 degrees Celsius. Yes, what is your question?
So, but if you keep your temperature low, the reaction will oppose your thing, na? So it will automatically rise.
The reaction will not start only, because nitrogen cannot be broken down only. If the reaction does not start, then nothing is going to happen. So that's why I have to use this optimum temperature.
Oh, okay, sir. Got it.
The last part is about the catalyst. Now see, if you are using a catalyst, okay, catalyst, what does it do? It provides a base. It provides a surface area for the reactants to combine together. Okay, basically what the catalyst is going to do, suppose you are having a substance A, you are having a substance B, this is your catalyst, that is substance C. Okay, A will be brought over here, B will be brought over here. It is going to form a surface or a medium at which they can react. Once A and B have combined together, this A and B will go away. This is what a catalyst is going to do. Okay, but at the same time here, this catalyst, also ammonia is also present over here. So this ammonia also can break down back to nitrogen and hydrogen at the same place. That's why a catalyst does not affect the rate of reaction. What only it does is the equilibrium which is there, it can be achieved quickly. That is the purpose. Okay, so that the equilibrium is achieved quickly. That's why we are going to use catalyst. What is the catalyst that is used over here? The catalyst that is used over here is finely divided ion. Okay, of course here platinum also can be used as catalyst, but that's expensive. So iron is used as a catalyst, as I've said, that a catalyst merely helps to achieve the equilibrium quickly. Because the reaction is reversible, it does not affect the rate of reaction. If you have any doubts or questions, you can ask me. Okay, the purpose of using catalyst is that equilibrium is achieved quickly, so that immediately, because ammonia can be easily compressed and it can be removed. Once it is removed from the reaction mixture, then more of nitrogen and hydrogen are left. So again the equilibrium will shift towards right, and again we are going to get more of ammonia. Because ammonia is a gas whose properties are different from nitrogen and hydrogen. These both gases are not compressible, and their boiling points are also very low. This ammonia gas which is there, easily you can liquefy it, you can easily compress it, and you can remove it from the reaction mixture. Once ammonia is removed from the reaction mixture, the concentration of ammonia is reduced. So more of nitrogen and hydrogen will give us more of ammonia. Our target is getting more of ammonia. That is the purpose of manufacture of ammonia, that is of Habers process. That's why we are using a catalyst, so that equilibrium achieved is quickly. It is done at a quicker rate, so that we can get more of ammonia. I repeat once again more thing. One more thing I'm going to repeat once again, which is very important. For reversible reactions, catalyst does not affect the rate of reaction. They just help to achieve the equilibrium quickly. This is the purpose of using catalyst in a reversible reaction. When you say catalyst speeds up the reaction, this is applicable only for those reactions which are not reversible. And also one more important point, don't always think that the catalyst is always going to speed up the reaction. There are some substances which act as negative catalysts also. It means if that substance is present, the reaction will be slowed down or will not take place at all. Such substances are called negative catalysts. I'll just give you one example of it. Okay, we are having over here hydrogen peroxide H2O2. It decomposes into water and oxygen. Now, hydrogen peroxide is a mild bleaching agent. We don't want here water and oxygen, so I want this reaction to get slowed down. Sorry, this heat is not there. Okay, if heat is there, obviously if the decomposition will be faster. I don't want water and oxygen, because this oxygen will escape out into the atmosphere, and what will remain in the bottle will be only water. So this reaction has to be slowed down. I want hydrogen peroxide, which can be used as a bleaching substance, mild bleaching substance. So in this case, we are adding another substance, some amount of phosphoric acid is added, so that this reaction is slowed down and preservation of H2O2 takes place at a longer time. Now this is a negative catalyst. It slows down the reaction. So always don't think that a catalyst is going to speed up the reaction. But these things are applicable only for those reactions which are not reversible. If you are talking about a reversible reaction such as Haber's process, it just merely achieves the equilibrium quickly.